Okay, good morning. So we have completed chapter 5, went over 5 examples. Your homework will also due tonight. There's 17, 18, 19, 20. So now we look at chapter 6. This is the last chapter in our in our syllabus, in our course material. And this has to do with frequency analysis. Okay, frequency analysis. So let's bring it up. All right, so far we have looked at circuits where we have a source on one side and we try to find the current or voltage at any given point in the circuit, right? Now we have to shift our viewpoint just a little bit. And the focus of this chapter is electronic filtering. Okay, electronic filtering. Now, electronic filtering works based on the frequency response of the capacitor and the inductor. And the principle continues on from chapter 5. Chapter 5, we learned about impedances of a capacitor and an inductor, right? Now, capacitors and inductors, again, repeating the same thing, is that they're energy storage devices. So if you apply an AC voltage or current to an inductor or capacitor, energy is continuously flowing in and out of these components. If you increase the frequency of the input, meaning the energy that is flowing in and out of the inductor and capacitor, the rate of energy transfer now increases. Okay. At some point, the inductor and capacitor cannot keep up. They cannot keep up with how fast the input is changing, right? So input changes, like say positive half cycle of the signal, energy flows into the inductor. Negative half cycle, it flows out. So if you have an inductor, positive half cycle, energy flows in, negative half cycle, energy flows out. If you have a capacitor, it's the exact opposite. Remember, impedance for a capacitor is negative. So in the positive half cycle, it flows out. In the negative half cycle, it flows in. This is an important concept that we will use later on. Okay. So again, depending on how high the frequency is, the rate of the energy transfer changes. And this principle is what we will use to filter out electronic filtering. Now, this table lists the frequencies of some most common electrical signals. Whether it is a wired circuit or a wireless circuit, electrical signals are present all around us. Okay. If you check around this room, even the devices that you're using, there are wires, there are cables that are carrying signals from, let's say, from your desktop computer to the monitor, from the desktop computer to the projector. If it's inside your laptop or smartphones or tablets, signals are being carried by wires that are embedded in the circuit board. Okay, so signals are being carried around from point A to point B to point C, D, and so on and so forth. I will give an example about wireless signals because those are the most common kind of signals that we see in everyday life. There are wireless signals all around us. If you reach your arms just out wide, your body acts like an antenna. You have AM radio signals, FM radio signals, television signals, mobile phone signals, cell phone towers, satellite signals, dish, DirecTV, for instance. And then, of course, there's wireless internet, home Wi-Fi. All of those signals are floating around us. Each of these signals, when I say signal, it's basically an electrical function, electrical signal, whether it's wired or wireless, is operating at a particular frequency. I've talked about how AM radio stations broadcast in the kilohertz range. FM radio stations broadcast in the megahertz range. The call sign of the radio station has a technical meaning behind it. The call sign of the radio station indicates the value of the frequency of the broadcast of that signal. So when you tune into 680 kilohertz or 680 AM, that is the broadcasting frequency of that AM radio station. So how do we ensure that all the signals that are around us do not interfere with each other? Well, we create a separate lane for each of one of these signals, okay? And we use a electronic device that acts like a gate, that acts like a filter. It blocks out the unwanted signals and only allows our wanted signal to come in, okay? So if it's an AM radio device, it will only allow or only permit select AM frequencies to pass through. Everything else is blocked. If you have an AM radio, and those still exist, if you have an AM radio, whether it's in a vehicle or handheld or whatever, it will block out any frequency signal that is outside of this AM range. So AM range is 540 to 1600 kilohertz. So below 540 kilohertz and above 1600 kilohertz are all blocked. A more common example I would like to use is your three big mobile phone companies. You have AT&T, Verizon, and T-Mobile. There are only three left, right? Three big ones that are the hardwired network. Each one of these operates at a particular frequency. And this frequency is governed or controlled by the government of each country. This is very precious. Okay, it's limited amounts. And so every few years, the government of every country auctions off this frequency spectrum. Think of it like a highway, and you are bidding on, like, it's like a 4-lane highway, and companies bid for the right to use a single particular lane of that highway. If they win, they have to pay money to the government. The government gives them the license to use that lane for themselves only. No one else is permitted to use that lane. Okay, so if you are Verizon and you bid on a particular frequency, it costs billions of dollars. And again, this is not just for the US. Every country around the world makes money like this. You have the right to send that signal at that particular frequency, and no one else does. Okay, and some frequencies are better at providing coverage, meaning they're better at penetrating concrete, they're better at penetrating metal structures, and that's why some companies have a better network than other companies. Okay, so AT&T, Verizon, and T-Mobile, well, T-Mobile purchased Sprint, so Sprint's frequency spectrum is now part of T-Mobile's, so they can provide better coverage. But if you have a Verizon phone, and nowadays it's still, they say it's like locked down. You cannot use it on any other network. So one of the things that they do is there's a filter at the front end of that phone. Okay, there's a filter at the front end of any phone, any wireless device. It'll block all signals except for the Verizon signal coming in. Everything else is blocked. There are many other circuits that are used to do this blocking, but this is the most basic and most common example. There's a filter circuit right at the front end of any wireless device, because if you hold up your phone or your tablet, perhaps, if you just hold it up like this, it's going to catch signals from every corporation, right? And so filters are the ones that actually block out unwanted signals and allow only your preferred signal to come in. Okay, any questions so far? Okay, so as I was saying earlier, we have to adjust the thinking just a little bit. So far, we have looked at circuits typically with a source drawn on the left, maybe a resistor, a capacitor, another resistor perhaps. Okay, and there might be a few other sources, but this is a simple circuit. And now we have to adjust our thinking a little bit. We are going to break up the portion and isolate the source on one side, put the circuit in the middle, and we extend a pair of terminals meaning a component across which we take the output. So for instance, if we take the output across the resistor on the far right, we will extend these terminals. All we are doing by extending is we are saying that we are placing our output load or whatever across that resistor. And now we will draw a box around that circuit. Okay. So sometimes in circuits, we buy off-the-shelf components. Okay. We have a circuit that is inside a sealed box. We don't know what it does. We don't know what is inside it. We don't know how it works. We don't have to analyze it. The only thing we care about is what it does. As long as we know what it does and the specifications related to that function, we can use that circuit. Does that make sense? Basically, our power supplies or multimeters. We know what it is, we know what it does, but we don't know exactly what is inside it, and we don't really need to know how it's going to work. It's a tool. We are going to use that circuit as a tool, right? We connect a power supply to a circuit, and we measure using a multimeter. So the left side of the circuit is basically classified as the input. Right side is output. Now, when I say left and right, I'm only referring to the circuit diagram. Like physical structure of a circuit like this could be anything. Could be up, top, left, right, doesn't really matter. But typically circuits are drawn with the input on the left and output on the right. And so we have a pair of terminals, plus minus on the left, plus minus on the right. We combine those terminals together and we call it a port, P-O-R-T, port. Port is anything that permits access. Okay, that permits access. So in real life, we have air port, sea port, electrical circuits. It's an electric port. So port is something that allows us access. So on the left side, the pair of terminals that we have, we combine them together and we call it the input port. And on the right, we say it's the output port. And in the middle is our network or our circuit. Network is another name for circuit. And we call it a two-terminal, two-port network. It's a two-port network. It has an input and it has an output. So in real life, you can buy filters that are like sealed boxes. You simply take it and you can design your circuit around it. Simply apply an input to it and you collect the output. So we have V in on the left, we have V out on the right. Both of those are AC circuits. If it's DC, then it doesn't change. So there is no frequency response for DC, right? Because the value is constant. It's only for AC that it works. So V in and V out, and I'm going to introduce a term that I created and I named it after me. H of F. You don't believe me? Yeah, neither do I. H of F is noted as a term called as transfer function. Transfer function. And simply put, a transfer function describes how an input is transferred to the output, meaning it is telling us what that circuit does. What is the function of that circuit? Okay, it is simply telling us what is the function of that circuit. How is it transferring the input to the output? And if you notice, both of these are in phasor form. So the input voltage and the output voltage are both in phasor form. Again, because they are AC signals, they are time-dependent AC signals. And so we're going to use phasor forms for both signals. And H of F is simply the ratio of the output voltage to the input voltage. Okay, ratio of output to input. And because it's a ratio, it doesn't have any units, it is dimensionless. But because it is a ratio of two phasors of two complex quantities, it has magnitude and it has phase, or theta of h. Okay, it has magnitude and it has phase. So at this point, let's take a pause. You think over all of that and let me know if you have any questions. Any questions so far from anyone? Okay. Let's see. Okay. All right. Let's look at an example. We are not given the circuit. We don't know what the circuit is. We don't know what the name of the circuit is. We don't know how it works. We are only given the transfer function of this circuit, and that too in graphical form. Okay, in graphical form. So we have the chart on the left, or the image on the left, which shows us the magnitude of h of f. And here, the image on the right shows us the phase. Okay, so you have magnitude on the left, phase on the right. Now, remember what I said. It's a sealed box. We don't know what is inside the box. We don't know how or why it works. We only know what it does. Again, remember, transfer function is something just describes the function of that circuit. How is it transferring the input to the output? We don't care about anything else. So let's say this kind of circuit, and I will go through this and then we'll take a break. We are asked to find the output if you're given a particular input. So we are asked to find, let's say, V out of t. If V in is if V in of t is, let's see, 3 plus 2 cos of 2000 pi t plus cos of 4000 pi t minus 70 degrees. Okay. 3 plus 2 cos 2000 pi t plus cos of 4000 pi t minus 70 degrees. That's our V in. It has 3 components. 3 components is relatively simple and straightforward. Remember, I just said, if you have your smartphone out, it's being bombarded with signals from all around. You have like multiple AM radio stations, multiple FM radio stations, multiple TV stations, multiple cell phone signals, Wi-Fi, everything's all around us, meaning it's all around our devices. So if we take a look and we write out the input into our smartphones, just lying on a table, there's like probably hundreds of signals that are actually going in there. So it'll be like 1 plus 2 plus 3 plus 4, hundreds of signals. So your smartphone is blocking everything out except for 1. And so if V in of t is 3 components, we'll break it up and analyze it at 1 at a time. So V in 1 of t is 3 volts. V in 2 is 2 cos 2000 pi t volts, and V in 3 is cos of 4000 pi t minus 70 volts. We are asked to find V out. Well, we use phasor operations from chapter 5 to find V out, because H of F is the phasor of V out over V in. Therefore, I can write that V out is simply the product of H of F times V in. That's it. Okay, H of F is the ratio of the voltages, output to input. So if we know the input, we can predict what our output is going to be. Does that make sense? If we know the transfer function, sorry, not if we know the input. If we know the transfer function, meaning if we know what that circuit does, we can predict what the output would be no matter what the input is. Does that make sense? Right? So H of F is known to us. It is given in graphical form. And so we'll write out the transfer function for each one of these input frequencies based on these charts. And then we simply multiply it with the input, and we can get or obtain our output. Does that make sense to everyone? Right? Okay, so I'm going to write out frequency values. F1 is 0 hertz because it's DC. There is no time dependency. So frequency for first component is 0 hertz. F2, omega divided by 2 pi. So 2000 pi divided by 2 pi gives me 1000 hertz. In F3, 4000 pi divided by 2 pi, 2000 hertz. The reason I am converting to hertz is because my chart is also in hertz. Okay. This should have magnitude symbol right there. So magnitude of H of F and angle of H of F. So let's find out what the value of H of 0 is. What is it at 0 hertz? Magnitude is 4. Phase angle is 0. So 4 with an angle of 0, or simply 4. Make sense? We simply read the chart at the frequency that we want. H of 1000. So it's right here. Three with an angle of 30. And H of 2000. 2 with an angle of 60. Let's take a pause. Let me know if you have any questions. Yes. This one? Oh, that's the problem statement. Sorry. So problem statement. Calculate V out of t if V in of t is, and given that way. All right, any questions? Other questions? Okay, then let's write out the phasors for V in 1. Wait, we already have. No, we didn't write out the phasors. So let me write it out here. V in 1 would simply be 3. V in 2 would be 2 with an angle of 0. And V in 3 would be 1 with an angle of minus 70. Okay. Volts, volts, volts. So now V out to 1 would be H of 0 times V in 1. H of 0 is 4 times V in 1, 3 gives me 12 volts. V out 2 would be H of 1000 times V in 2. It's 3 angle 30 times 2 angle 0 gives me 6 with an angle of 30 degrees volts. And V out 3 is H of 2000 times V in 3. Two angle 60 times 1 angle minus 70 is equal to 2 with an angle of minus 10. Still continuing on from the phasors, we use the exact same techniques. Magnitudes are multiplied, phase angles are added up. And your final answer is being asked as a function of time. So V out of t, you would again add them all up. Okay, just write it out exactly as the input problem statement. So 6 cos of 2000 pi t, frequency does not change. So frequency remains the same. Only the amplitude and phase is affected. This is volts. And that's your final answer. Let's take a long break, longer pause. While you think over this, let me know if you have any questions. Review the steps and then compare the input and the output. What insights can you glean? What do you think is happening to the input? Specifically, look at the magnitude or the amplitude of the signals, each one of those components.
Can you scroll up and right a little bit, please?
Sorry, what?
Can you scroll up and right a little bit,
Oh,
please?
scroll up and right. Okay, there we go. Hold on.
Cool, thank you.
Okay. So let me make it slightly smaller so that everything is captured in one screen. Is that better? Okay, so we have V in of t at the top right and V out of t at the bottom left. What do you notice about the values? Let's take a look at V in 1. V in 1 is 3 volts. What is V out 1? 12. So what is it that the circuit is doing? What is that network doing? Making it bigger. In technical terms, it is amplifying. It's amplifying the signal. And when it comes to wireless signals, especially wireless signals, as soon as they transfer out from the transmitter, they get weak because loss occurs when it's transferred through the air. So by the time the wireless signal does reach our receivers, the signal is very, very weak. So in addition to filtering, we also have a small amplifying section at the front. It's also known as the preamplifier. It'll take the relatively weak signal and impart some strength to it. Okay, so the circuit, again, we don't know what it is, how it works, or why. We can deduce or we can conclude that it is an amplifier for a certain frequency. Even the other two components, V in 2 and V in 3, 2 volts goes to 6. 2 volts goes to 6. And for V in 3, 1 volt goes to 2. So all three components are being amplified. All three frequency inputs are being amplified. They are being made stronger. They have higher magnitude. Not at the same length, of course, not at the same strength, but it's being amplified. All frequencies above, let's see here, let's mark this as 2500. So all frequencies above 2500 are reduced to 0. So if there were hundreds of components in V in of t, and all of them, or apart from these three, all of them had a frequency that was above 2500, they would all be reduced to 0, filtered out, blocked. Does that make sense? Right, questions? Did the procedure make sense? So your next homework assignment is exactly the same problem. Well, when I say exactly the same, as in like the steps and the approach is exactly the same. The only difference is that V in of t is different and your graph values are different. There's only 1 or 2 problems in that entire assignment. It's homework number, I can't remember, it's either 17 or 17, I believe. Okay, homework number 17. Only 2 problems. While the material is still fresh today, get it done. It shouldn't take you longer than 30 minutes of your time to get it done. Okay, so get that homework number 17 done so you don't have to wait till tomorrow. And then homework 18, I have removed from the course syllabus. So homework 18 is not, we're not going to do homework 18. We'll skip directly to homework 19, which is resonance circuits. So I will still discuss the material and everything, but you won't have to do a homework regarding that. But any questions about this problem before I move on? Okay, let's take a break, a very short break. It's 11:13. Let's take a break of, I don't know, 3-4 minutes, 11:17. Let's pick up again at 11:17. In the meantime, if anyone has any questions, I'm here.